I grew up in Detroit, not a suburb of Detroit, but actually Detroit, which is important. I was really interested in nature. I had a tendency to go out in the backyard, pick up leaves and sticks, poke at ants, pull leaves apart so that you can see how they're structured.
Graduating high school at just 16, Paula Hammond left her hometown for MIT and her first look at the deep complexities of nature's building blocks. Today, she's a world-renowned chemical engineer.
I think of myself as an interested, curious, excited and engaged human who really gets excited about science and how science can make a difference in human lives.
From fuel to medicine to agriculture, chemical engineers design processes and machines that influence humanity on a global scale. Back in the mid-90s, as a young researcher at MIT, Hammond was dreaming up a new class of machine, tiny molecular-scale chemical devices built one layer at a time.
It's like building a skyscraper from structurally dissimilar floors. First, a little polymer chemistry to fashion the many planes of repeating molecules she'd need. This one, an insulator. That one, conductive in just the right way. Then the tricky part, riveting the incompatible layers together by alternating electrical charges, all stuck together because opposites attract. The result? A battery electrode a few molecules thick, a barely visible transparent film. But it was Hammond's mastery of the layer-by-layer assembly process that earned renown.
I think of myself as a molecular engineer. We build from the ground up, layer by layer, function by function, producing films far thinner than a human hair. In them, I see a new future for medicine.
Today, at the Koch Institute for Cancer Research, Hammond's films are debuting as trailblazing biomedical implants, capable of adhering to organs, skin, bone, and more.
And it turns out that these films are so thin and they're able to conform to any shape. We can coat virtually anything with them.
In a breakthrough almost certain to revolutionize medicine, Hammond layers the films with special protein molecules that recruit stem cells and engage the body's natural repair mechanisms.
We can actually design materials that can help a joint repair more rapidly. We can coat, for example, a very simple degradable scaffold with thin films that help generate bone.
In the near term, Hammond has high hopes to bring a new treatment for ovarian cancer to the 300,000 women diagnosed each year, as well as a gene-editing biofilm that could cure sickle cell anemia for 20 million people around the globe.
I think that one of the things that has made me happiest when I look over my career is how I have impacted the lives of others. And that for me is what gives me that feel-good feeling, even more than the incredible discovery in lab, which has always been a feel-good feeling.